Hi, this is TheoryStation and I'm John Duggan. This program is called Rational Choice Modeling. The series that we're on is the Basic Formal Theory Toolkit, and this is installment 3 in the series. So in the last couple installments we talked about the model of preference and choice, and here we're going to really talk about a special case of that, but it's cost-benefit analysis. Again, the point of this series is to think about, just cover the bread and butter models of rational choice modeling, and this is definitely one of them. So in the cost-benefit analysis model, we have we have a decision maker. You can think of it as an agency, or it could be a firm that is choosing some non-negative number, which you can think of as the scale of a project. Okay, so you can either basically not do the project, you can do it at 0 scale, or you can choose a higher scale that's positive. Of course, you'd have to, in an application, you would have to choose units, and so maybe that's time or miles of roads or dollars spent. For this, I'm just going to assume some units are chosen. And so again, we need a set of conceivable alternatives, and these are going to be, they have to be non-negative, and I'm going to I'll use little x's and little y's for the scale of a project. So, So we're going to assume that whatever choice is made, it has to be non-negative. Okay, so now that's not a very interesting model yet. We have to have some way of evaluating the cost and benefits of any choice. And so we're basically just going to have 2 functions, and instead of an f, I'll use a b for the benefit function, right? So this is, it's a function that takes the scale of a project and it gives us the benefits from that project scale. Again, measured in some units. They could be dollar amounts, but that's not necessary. So this is the benefit from x. And we're also going to have a measure of cost. So there's a cost function. We'll use the notation C for that. And right, and so of course in an application we'll be imposing some structure on these functions. The natural one is that it wouldn't have to be like this necessarily, but in a typical application we would assume that the benefit function is increasing. So higher project scale is better. At the same time though, a higher project scale costs more. So we would often assume that B and C are both increasing functions, and we might assume something about their curvature. So B might be an increasing function, but it's getting flatter as the project scale increases. And so if this is our function B, that would be, that curvature assumption is the assumption of diminishing marginal benefit. The cost function typically would be assumed to be increasing again, but also shaped in a convex way. And that assumption is called increasing marginal cost. Okay, so That's kind of what the typical setup of the model looks like. Now, what actually makes the model go and give us either a prediction or a recommendation, depending on the use, is we assume that the decision maker is going to, wants to choose this level of scale to maximize benefit net of costs. So we're going to choose some non-negative scale, some non-negative scale to maximize benefit minus cost. So if you, if we go back to the previous installment where I talked about a utility function, this net benefit function is basically, that is the utility function of our decision maker in the cost benefit application. Okay, so we want to maximize net benefit. So that's the general cost benefit model. So with that, let's just dig in a little bit to see if we can get some intuition. And here I'm going to just maintain this assumption about increasing marginal cost and diminishing marginal benefit. To get an idea of what's going on, let's choose a scale x like so in this graph. At x, we can go up and we can read the benefit from x and the cost, and the net benefit is going to be the difference between these two curves. We can choose another scale, y. We can do the same thing, and again, the net benefit is going to be the difference between the two curves. For these choices, you can see the net benefit is positive, but in fact, the scale x is better than y because the net benefit's bigger. But neither of those choices are going to be optimal. In fact, if we chose, looks like about here, if we chose this level, let's call it x star. Star will denote something good. At that scale, it looks like the difference is, it's bigger than it is at x, and it's about as big as we're going to get it. Okay? So that's kind of what an optimal choice looks like. Right? If we go into this a little bit more deeply, let's think about how the benefit and cost function would change if we increase the scale a little bit starting at x star. Okay? So we're at this optimal level of scale. We increase the scale a little bit. What's the rate at which the benefit changes? Well, we can get that by the slope of this tangent line right above x star. The slope of that tangent line, that's the derivative of the benefit function at x star. And that gives us the rate of change of benefit if we were to vary our scale level a little bit right at x star. What's the rate at which cost would increase? Well, we can get that by drawing the tangent line again right at x star. The slope of that line is going to tell us the rate at which cost changes if we increase the scale a little bit at x star, and that slope is the derivative of the cost function at x star again. Little sidebar here, just some terminology. So at any scale level, x, the derivative of the benefit function at x, we call that the marginal benefit at x. Marginal referring to some small change, and the derivative of the cost function at x is the marginal cost at x. So going back to the graph here, we can see the marginal benefit at x star. It's just the slope of this tangent line. The marginal cost is the slope of the lower tangent line. And if I had drawn this graph perfectly, those two lines would be exactly parallel, meaning that the marginal benefit and the marginal cost at that optimal scale level are the same. That is something that, it's an intuition we get from this picture. So it's, based in a geometric intuition, but it's something that we can derive formally if we go back to this maximization problem here that our decision maker is trying to solve. So just from basic calculus, we know that in general, if you're maximizing a function, that at a local maximizer of that function that's not on the boundary of the domain, the derivative is equal to 0. All right. Well, in this context, if we have an optimal scale level like x star that's positive, as it is in this picture, that it's called the first order condition. That tells us that the derivative of the objective function evaluated at x star has to equal 0. Here we're differentiating the difference between the benefit and cost function. So calculus tells us that at a positive optimal scale level, the derivative of the net benefit function must equal 0. From the and here I'm using the Leibnizian notation for a derivative. From the sum rule, we know that this derivative of net benefit, that is just the derivative of the benefit function minus the derivative of the cost function. Okay, so I've just rewritten the left-hand side here. If I switch to the Newtonian notation, well, we would just write primes for derivatives then. And, well, now I can just add c prime of x star to both sides, and the first order condition then gives me this equality, which is exactly what we saw in our diagram. Okay, so that geometric intuition comes right out of calculus, and it tells us, in the cost-benefit context, a rational decision maker will equate the marginal benefit and the marginal cost of the scale of this project. Intuitively, if those weren't the same, if the marginal benefit, let's say, were bigger than the marginal cost, well, then you could actually do better by just increasing the scale a little bit. If the marginal benefit were lower than the marginal cost, you could decrease the scale and be better off. So that's sort of how you would apply calculus to get that intuition in a formal way. And let's just stick with this for a little bit longer, and let's go to an explicit example with functional forms. Again, it's just digging a little bit more deeply and seeing how calculus can be helpful here. So let's do an example where the benefit function has the form, let's go with just a linear form here, where beta is just a fixed parameter, and it's going to be positive. the cost function is gamma times x to the alpha, and here gamma is also a fixed parameter, and alpha is a fixed parameter. Gamma is positive, and I'm going to assume that alpha is strictly bigger than 1, which is going to give us the increasing marginal cost. So the cost function will have a shape like this. The benefit function, actually, in this example, is just going to be a straight line. Okay, and just intuitively we can see that the optimal scale will be something like this. And I should just say, the idea of introducing parameters is a way of making the model somewhat general. Okay, the shapes of these functions aren't really going to change in an essential way, but the exact form, we have control of the exact form by just playing with these parameters. So anyway, but just for arbitrary parameters then, let's think about the cost-benefit problem. So we're going to choose a level of scale to maximize benefit net of costs. And so how do we find this optimal scale? Well, assuming for the sake of argument that it's positive, and it will be, again, we know from the first order condition that we did on the previous slide, we know that the derivative of the net benefit function has to equal 0, or marginal benefit has to equal marginal cost, and that is when evaluated at the optimal scale. Okay, so all right, so what is the derivative of the benefit function? Well, because it's linear, it's always beta. It doesn't depend on where we evaluate that derivative. The derivative of the cost function is going to be, well, to evaluate this thing, we drop the exponent down and subtract 1. Again, that's evaluated at x star. So the first order condition for this problem is going to be like so. We can solve for that if we just let's divide both sides by alpha times gamma. And you can see why we need alpha and gamma to both be positive to do this. And then we're going to raise each side to the power 1 over alpha minus 1. And here we're using the assumption that alpha is bigger than 1. And then if I just switch sides of the equation here, we get this form for x star. It is beta over alpha times gamma, quantity raised to the 1 over alpha minus 1. This is a parametric solution for the optimal level of scale in this special cost-benefit example. It shows you how we can use calculus techniques to solve a problem like this in an explicit way. Notice that a nice thing about this is that even though there's a lot of structure on the problem, it is somewhat general because we have 3 different parameters that we can play around with. And we can do thought experiments. We called those comparative statics previously, but we can think about changing some element of the model and seeing how the conclusion of the model changes. So for example, suppose we increase this coefficient beta in the cost function. Well, diagrammatically, what we're doing is we're making this curve, this benefit curve, steeper, and that's going to, change that optimal level of scale. In the picture, it's going to be something bigger, like so, and but that's not just true in the picture, because we have this general, parameterized solution for the optimal scale. We can just see that, here's where beta enters in. If that beta gets bigger, that fraction gets bigger, and 1 over alpha minus 1 isn't going to be an increasing function, so x star will increase. We can write that like so. The derivative of x star with respect to beta is positive. We could do the same exercise with gamma, and not surprisingly, that's going to, if it becomes more costly to build scale, then you're not going to do as much at the optimal solution. So the derivative of x star with respect to gamma is going to be negative. Alpha is more complicated. It's going to, if we vary alpha, that's going to change this the shape of the cost function curve, and that sign of that derivative is actually going to depend on the other parameters as well. So I'm not going to bother with that one. But this is an example of one of our bread and butter models, the cost-benefit model, and how you can go about solving it. And this idea of equating marginal benefit, marginal cost is one that is, it permeates rational choice modeling. So that's it for this installment. And in the next one, we'll be thinking about one that's a little bit more politics oriented.